So far during this class, we spent a lot of time talking about reaction mechanisms, and we spent a lot of time talking about synthesis, reactions, forming new carbon-carbon bonds, or interchanging functional groups. Now I'm going to turn our attention to the third big thing that organic chemists look at, which is structure determination by spectroscopy. If you have a compound of interest isolated from a biological source, for example, that may have a pharmaceutical benefit, before you can go about synthesizing it, you have to know what it looks like. And that's where spectroscopy falls in. Most of the time we find things out about chemicals or about nature by shining light at various wavelengths at it and observing what happens. So we need to have a familiarity with the electromagnetic spectrum. And with what regions of the electromagnetic spectrum cause specific types of transformations within a molecule. So you probably know that the visible range goes from about 400 on the violet end to about 800 to 850 on the red. And some people can see further out into the red than others. And that beyond these are nanometers. So, and that beyond the red, we get to infrared radiation. And if we keep going, we have microwave radiation. And then we have TV and radio. And we might have 1 to 10 meter wavelengths up around there. The cutoffs are not exact, but the infrared range generally ranges from here 850 nanometers to approximately 1 millimeter up to about 100 millimeters. And then the microwave, 100 micrometers. And then 1 micrometer up to about 100 micrometers. And then the microwave range goes from about 100 micrometers to 100 millimeters or so. And then you go beyond there, the microwave to TV is also not really fixed. In the infrared range, we are looking at a change in vibrational energy levels. So it's often referred to as vibrational spectroscopy. We're causing a bond and we're making it expand and contract, or maybe we're making that bond bend. Infrared is heat, right? And when you heat molecules, they start vibrating. In the microwave range, we're talking about changes in rotational energy levels. You're making molecules spin. So microwave radiation and infrared heat radiation cook your food in fundamentally different ways. Microwave radiation by making your water molecules spin. Infrared radiation by making your water molecules and other molecules vibrate back and forth so the bonds expand and contract. So we're looking at lower energy transitions here, longer wavelength, right? Remember that E is equal to H times C over lambda. So there's an inverse relationship between energy and wavelength. And E equals H nu, so there's a linear relationship between frequency and energy. So we're talking about relatively low frequency, low energy transitions to rotate molecules, slightly higher frequency, higher energy, shorter wavelength to vibrate molecules. And in the visible and UV range, the ultraviolet visible range, which goes somewhere from about 50 nanometers to 200 nanometers in the far in the near UV. This range here is a change in electronic energy levels. Ultraviolet visible light actually takes an electron and promotes it from one orbital to a higher energy orbital. And then further down from ultraviolet and visible, we have X-rays and gamma rays. The difference between X-rays and gamma rays are generated from the nucleus. But in the kind of very short wavelength region, X-rays and gamma rays overlap and have the same wavelength. It's just a matter of where it comes from. So gamma rays come from the nucleus when there's a nuclear decay of a radioactive nuclide, whereas X-rays are derived from the electronic part of the molecule by exposing it to electric field and causing or bombarding it with electrons. And then in the very short wavelength, we have cosmic rays. These are referred to as ionizing radiation. Because we have the ability to take the electron and remove it completely from the atom to form ions, and it can be very damaging. Anything beyond the near UV, in the far UV, X-rays, gamma rays can be very damaging to skin and cause cancer, and require some kind of lead shielding. And these are very short wavelengths. These can be just in the picometer range. It is possible some spectroscopy is done in the gamma ray Mossbauer spectroscopy. Looks at nuclear energy levels. Much like ultraviolet and visible spectroscopy looks at electronic energy levels, nuclear energy levels are further apart, and so they give off higher energy, shorter wavelength, higher frequency radiation. So you can look at the gamma rays that are emitted from a nucleus, and Dr. Harry Kay, who's doing that work, he's a nuclear physicist, using gamma ray spectroscopy to investigate nuclear energy states. So we're not really interested in this part of the spectroscopy at the moment. IR spectroscopy is one of the types that's very useful for organic chemists, so we'll talk about that a little later. That's in chapter 11. But right now I want to focus on this end of the spectrum, the very low energy, long wavelength, and low energy, low frequency area, because nuclear magnetic resonance spectroscopy, which is the primo spectroscopy for structure determination in organic chemistry, works in the radio frequency region. And it's abbreviated Nmr Spectroscopy. And what nuclear magnetic resonance spectroscopy tells us is about nuclear spin states. Not nuclear energy levels, right? That's the very short wavelength side, the gamma ray spectroscopy, the Mossbauer spectroscopy. But nuclear spin states. Nuclei, like electrons, can have more than one possible spin states. All electrons have a spin quantum number that's either +1/2 or -1/2. Many nuclei also have just two spin states that can be called +1/2 or -1/2, or the alpha and the beta state. But other nuclei have what's called a quadrupole nucleus, and they might have three nuclear spin states, +1, 0, and -1. Or they might have a nuclear spin state of +7/2, in which case they would have +7/2, +5/2, +3/2, +1/2, and 8 possible spin states. Most of the nuclei that we're most interested in protium, the most abundant isotope of hydrogen, carbon-13, which is the small natural abundance isotope, about 1% natural abundance of carbon, 31 phosphorus, which is the major isotope of phosphorus, 19 fluorine, which is the major isotope of fluorine. These all have spin 1/2. Which means they have two possible spin states. Just like an electron, plus 1/2, minus 1/2. In the radio frequency range, you can also do electron spin resonance spectroscopy, ESR, which gives you information about electron spin, but that's really only useful for radicals, for things with unpaired electrons, whereas Nmr spectroscopy is useful for all kinds of organic molecules. MRI is derived in the same region. It is basically a nuclear magnetic resonance experiment. It's called magnetic resonance imaging instead of nuclear magnetic resonance imaging because the general public doesn't understand what nuclear means, and so they're intimidated by nuclear, and magnetic resonance imaging sounds better. Basically what magnetic resonance imaging is looking for is regions in the body that have a lot of water, which has two hydrogens attached to it. So it'll light up pretty bright by nuclear magnetic resonance spectroscopy because Nmr spectroscopy is good at finding protons. And many diseases are associated with changes in water concentration within cells. So you can look for cells that are doing a lot of rapid metabolism using MRI spectroscopy, or injured cells that are producing a lot of water in the repair process. It's relatively low resolution though, because the resolution that you're able to achieve using nuclear magnetic resonance spectroscopy is very much dependent on the homogeneity of the magnetic field. And it's impossible to get a really homogeneous magnetic field over the volume of space typical of the average human. You can get a really, really nice homogeneous magnetic field over just a small region of space, which is suitable for small samples in organic chemistry. The other catch is that the sample in nuclear magnetic resonance spectroscopy is generally spinning at about 20 cycles per second, and most people would probably object to being spun at 20 cycles per second. So in MRI instruments, the magnet is spinning instead of the person, and when you spin a magnet like that, you very much decrease the homogeneity of the magnetic field that's achievable. So we're going to talk about Nmr spectroscopy. And 13C, because those are the forms of Nmr spectroscopy that you're going to be working with. And you can talk in the nuclei, because they're both spin 1/2 nuclei, about having a plus 1/2 and a minus 1/2 spin state, or an alpha and a beta spin state. By convention, the lower energy spin state is called alpha, and the higher energy spin state is called beta. But that's just convention. So normally what happens when you have a nucleus is it's spinning. Just like electrons, the nucleus has a spin. And that nuclear spin is random. You can have that nuclear spin on any axis. In the absence of magnetic field, you're just going to have your nuclei randomly spinning. If you put your nucleus in the presence of a strong magnetic field, which if you're a physicist, you will refer to as B0, and if you're a chemist, you'll refer to as H0. Some chemistry textbooks use E0, but most of the time we don't really want to talk to other disciplines. So we use a completely different symbol just to throw them off the tail, right? So we have this applied magnetic field, and in the magnet that we have upstairs, that applied magnetic field is 70,000 Gauss, or about 7 Tesla, which is a very strong magnetic field, enough to stop a pacemaker, enough to demagnetize a credit card or a flash drive, something you don't really want to get too close to for too long. With this strong applied magnetic field, the nucleus has a choice of aligning its spin so that it lines up with, or aligning its spin so that it opposes. Under the normal conditions, when you have spinning on a random axis, you have no energy difference. Between any of these nuclei that are spinning in their random direction. But once you force them to either align with or align against the magnetic field, you do have an energy gap between the alpha and the beta spin state. It's not a very large energy gap, which means that it's about a 50-50 ratio. About 51% will take the alpha spin state, about 49% will take the beta spin state, and we usually show those with up arrows for the alpha spin state and down arrows for the beta spin state. And this energy gap is dependent on gamma, the gyromagnetic ratio, for the nucleus. And for a proton, that's 26,753 Gauss to the -1, seconds to the -1. And it's different for every nucleus, times Planck's constant over 2 pi, times H0 B0, where this is the applied field. And H is Planck's constant. Which you might remember is 2.34. So I don't think that is Planck's constant. I don't remember what Planck's constant is right now. I'll think of it at some point. Since E is equal to h nu, and there's an h here, we can plug in h nu for delta E, cancel out the h, and discover that the frequency is equal to gamma times 1/2 pi times h0. And for our field of 70,000 Gauss, and the proton magnetic resonance of 26,753 Gauss to the -1 seconds to the -1, we discover that the frequency is about 300 megahertz, or 300 times 10 to the 6 seconds to the -1, where 1 hertz equals 1 second to the -1. So we're talking about a 300 megahertz energy or frequency for that energy gap between the alpha and the beta state for proton. For carbon, we're talking about 75 megahertz. For our magnet, the 70,000 Gauss or 7 Tesla magnet. The carbon resonance frequency is always 1/4 of the proton resonance frequency. So if you're working with a higher field magnet, which would be 500 megahertz for proton, it'll be 125 megahertz for carbon. Right? If you're working with something that's 100 megahertz for proton, it will be 25 megahertz for carbon. So there's always that ratio. And if you're curious, it's 120 megahertz for phosphorus 31, which might be relevant if you're working with nucleotides, things that have phosphorus in them. So one of the things that NMR spectroscopy can do is tell you what elements are present in your molecule. Because you can look in the 300 megahertz range to find out if there are protons, hydrogens in your molecule. You can look in the 75 megahertz range to find out if there are carbon-13, which means there would also be carbon-12. You can look in the 120 megahertz range to see if there's phosphorus. Chlorine-35 and chlorine-7 are both NMR active nuclei, and so you can find out if there's chlorine, bromine, 79 and 81 are NMR active nuclei. You can find out if there's bromine. But really, it's a very expensive, the one upstairs, if we were to replace it, would be about $280,000 at this point. It's a very expensive way of doing an elemental analysis, which can be done much more easily by mass spectrometry or by certain chemical tests burning it and looking for the presence of one of the products of combustion. The thing that makes NMR spectroscopy useful is not that it can tell you that there are protons in your molecule, which you probably already knew, but that it can tell you a lot about each proton. And when I say proton here, I'm talking about hydrogen, not about the protons that are in the nucleus of the carbon. We use proton NMR and 1H NMR kind of interchangeably. There are three pieces of information that are available. The first is the electronic environment around the nucleus. Because electrons are charged particles, they interact with magnetic fields. And when they do that, moving charged particles generate a magnetic field of their own. And that magnetic field that's being generated by these moving charged particles, the electrons, is called H-induced, or H-I, or H-local, H-LOC, and that magnetic field will add to the applied field, or subtract from the applied field, and change the magnetic field that's actually felt at the nucleus. So if you look in the 300 megahertz range, but you look at high resolution, you can determine what the electronic environment, how many electrons there are, whether there's an electromagnetic element withdrawing electron density from that, by looking at the slight changes in the frequency. If you have a very large applied field, and you have your nucleus, there will be electrons circulating as a result of the applied field. The right-hand rule applies here, and those electrons will circulate in such a way as to generate an induced field or a local magnetic field whose lines of force oppose the applied field in the center and reinforce it out here. If we take this magnetic field vector that's being generated and add it to the applied field, we will get an effective magnetic field I just abbreviated H. Effective. And you'll see that H effective is less than H naught, the applied field. That's referred to as shielding. The electrons are shielding the nucleus from the full effect of the applied field by giving them a little bit of a magnetic field, very small compared to the 70,000 Gauss, but a little bit of magnetic field that opposes the applied field, yielding a slightly smaller effective magnetic field. The more electron density you have, the stronger this local or induced field will be. And that equals more shielding. If you have a reduced electron density, and you might have that because of an electronegative element pulling electron density away. You will then have a smaller electron density, which means you will have a weaker, right, base local. Or HI, H reduced, which means you'll have less shielding or more de-shielding. So we refer to the nucleus as either being shielded or being de-shielded, depending on whether there are elements near it that are pushing electron density towards it or pulling electron density away from it. And most of the time we're looking for oxygen or nitrogen or halogens, which will all pull electron density away and cause this de-shielding. So that's the first piece of information you can get. You can get the electronic environment. It's important, though, that we be able to talk to each other about spectroscopy, and when we give a number for the location of the nucleus, that we have a number that's independent of the instrument we're running it on. So we want a field-independent number that doesn't depend on how much money we have and how big a magnet we can afford. And we want to have a reference that we can set equal to 0 on that scale, and then have everything else on the scale. So we use a field-independent scale which is called delta, and has units of ppm. It's called the chemical shift, and it's defined as the shift downfield, which is in the region that's de-shielded from the internal standard, in hertz, divided by the spectrometer frequency expressed in megahertz. And that's where it comes parts per million, because 1 megahertz is 1 million hertz. So the shift downfield in hertz divided by the spectrometer frequency in megahertz gives you units of parts per million from the internal standard. Right? So we need a field-dependent scale, and we need an internal standard. Which will set delta equals 0 parts per million, and then we'll refer to everything relative to that. And the internal standard is TMS, which is tetramethylsilane, which is a tetrahedral compound which has 4 identical CH3 groups attached to silicon. It's very volatile, which means it's easy to remove later from your sample. Hard to pipette, in fact, because it's so volatile that just the heat of your hand will tend to evaporate it. It has 12 identical hydrogens. Which means it gives a very strong signal. Means you don't need very much of it, typically 0.03% by mass will give enough of a peak to see it. And it's about as shielded as possible, because silicon is less electronegative than carbon. The dipoles lie this direction. And because these are so heavily shielded, there are few things that have negative chemical shifts. So we don't have to worry about positive and negative numbers. In phosphorus NMR, that's not true, because phosphoric acid, which is what they use as the internal standard, is in the middle of the range of phosphorus chemical shifts. So you have both positive and negative chemical shifts. But in both carbon and proton NMR, we use tetramethylsilane because it's about as shielded as you can get for both carbon and proton. So the chemical shift is the shift downfield from the internal standard, which is tetramethylsilane, in hertz divided by the spectrometer frequency in megahertz. For our instrument, that means that a chemical shift of 1.0 is 300 hertz away from the TMS peak. And a chemical shift of 10 is about 3,000 hertz away from the TMS peak. The chemical shift is what tells us about the electronic environment. So that's the first piece of information, the electronic environment, which we determine by looking at the value for the chemical shift. Typical chemical shifts for proton NMR are between 0 and about 13. And really most of them between 0 and 10. For carbon NMR, typical chemical shifts that we look at are between 0 and 210 or so. So the carbon chemical shift range is much larger than proton chemical shift range. And you'll need to learn the proximate chemical shift values for the types of proton that we're normally looking at. So if we look at our chemical shift scale from 0 to 13, we know that at 0, we have TMS. In the range from about 0.7 to kind of 1.5-ish alkyl groups. And at 0.9 ppm is the typical chemical shift for a tert butyl group. In the range at around 1.5 ppm-ish is where we would see something adjacent to a carbon-carbon bond, not the protons directly attached to the carbon-carbon bond, but like a CH3, something in a position alpha to the carbon-carbon bond. At 2.1, that's the typical chemical shift for a methyl group attached to a carbon-oxygen double bond. So acetone, for example, will show up with a nice singlet, a single sharp peak at 2.1 ppm. And when you have a big peak at 2.1 ppm, I know that's because you clean your tube and just let it dry before you ran your spectrum. In this range from 3 to 4, kind of expanding a little bit further, this is where we typically see hydrogens that are attached to carbon adjacent to oxygen. So the CH2 or CH group that's attached to an oxygen or chlorine. And we typically see those in that 3 to 4.5 range. In this range here, around 5 to 6, that's where we see the hydrogens that are directly attached to a carbon-carbon double bond as opposed to in the alpha position. In the 7 to 8 region, that's where we see hydrogens that are attached to a benzene ring. In this region from 9 to 10 is where we see hydrogens that are attached directly to a carbon-oxygen double bond. Right? 2.1, they're attached in the alpha position. 9 to 10, they're attached directly right onto the carbon-oxygen double bond. And then in this region here is where we often see carboxylic acid hydrogens. So carboxylic acid is the furthest downfield, followed by aldehydes, followed by aromatics. Followed by alkenes. Followed by alcohols and alkyl halides. And if you're attached to bromine or sulfur, something that's a little less electronegative than the oxygen or chlorine, you're kind of in this range here where you're a little bit less far downfield, maybe 2.5 to 3.5. Alkynes, alkynyl hydrogens, kind of show up in this range of 2.5 plus or minus 0.5-ish. And CH3 groups that are attached to an aromatic also show up in that general range. 2.3 maybe. And so you see that a little bit further downfield than you see a CH3 that's attached to a carbon-oxygen double bond, which you see a little bit further downfield than the CH3 that's attached to a carbon-carbon double bond. And then your plain old alkyl groups. Primary or methyl groups are on the low end of this in the 0.9 range. Methylene groups maybe go down a little further to maybe 1.1. Methine groups where you have like here, like this hydrogen, that would be down closer to maybe 1.3. But typically, you're not going to be able to tell the difference between primary, secondary, and tertiary alkyl groups. They're all in this kind of region right about 1 part per million. Much more useful, carboxylic acid versus aldehydes, aromatics, alkenes, and the alcohols and alkyl halides, because they're in rather distinct regions. In the carbon NMR, they're in about the same general area, right? But of course the numbers are bigger. So carbonyl compounds, ketones, and aldehydes are about 210 part per million. Esters, carbonyls, there's another oxygen here, those are about 170 ppm. Aromatics are in the region from like 120 to 150 ppm, right? And then alkenes are a little bit further up, but overlapping with the aromatics. And then if you look at the alcohols and the alkyl halides in the carbon NMR, you'll find that these are typically in that 50 to 75 range-ish. And acetone is about 30 ppm, right? And then your alkyl groups are kind of in the 0 to 20, maybe 5 to 20 ppm for the alkyl. So you're looking about the same region of the spectrum. It's just that instead of a 0 to 13 scale, you'll be working with a 0 to approximately 215 scale. But the far left end will still be your carbon-oxygen double bond region, and then the next one over will be your carbon-carbon double bond region with aromatics a little further down than alkenes, and then the next region will be your hydrogen on carbon that's attached to electronegative elements, and then in this upfield range will be the carbons attached to hydrogen that's near, not on a double bond, but near a double bond, and then the furthest upfield will be the peaks that are just plain old alkyl groups. So down here, these are de-shielded and referred to as downfield. These are higher energy alpha beta gaps. Right, so you've got a larger delta E. On this end, this is referred to as shielded. This is upfield, and you're talking about lower energy alpha beta gaps. So your delta E is significantly smaller. Upfield, shielded, downfield, de-shielded, low energy, lots of electron density around the nucleus, high energy, much less electron density around the nucleus. And we'll talk a little bit later about why the aromatics and the alkenes and the things next to carbon-oxygen double bonds are so much further downfield than the carbon-carbon triple bond, or the things that just have an electronegative element. So that's the first thing, is the chemical shift. And in the next video, we'll talk about the other two pieces of information that you can get by looking at each signal, right? Where it is, the chemical shift,